Thank you. So thanks for the invitation. So my co-author on the paper, Asefa, she's a former PhD student. She's a postdoc at the University of Ottawa. And so actually she would have been here, but she has some health issues. Because actually she spends a lot of time in Montreal. Now about the project, so it is a bit work in progress, so that's an older paper, as I was telling some of you here. But it was kind of meandering for a while, and now, well, we think we have pretty decent results, but it's not finished, as you will probably see at the end, if I get to it, if I have enough time. So, yeah, and the other thing is, so it's kind of between two versions, so hopefully it won't be too confusing. Hopefully I'm not confused myself about where we are right now. So let me introduce the model. It's a what we call a house allocation model. So it's basically just a one-to-one kind of assignment. Each agent is assigned at most one object, and each object is assigned at most one agent. And we have a common ranking of the objects, which is fixed. So we have already an exogenously given ordering of the objects. We call this a common ranking. And we assume that, well, some parts is to be clear, but basically what we are interested in is when agents have a range of objects that is acceptable to them, or that is compatible, or they are eligible for according to this common ranking. Okay. And the common ranking is public information, and the assignments are based on the strict preferences of the agents over the objects. But what's really important is that the agents strictly rank the objects independently of the common ranking. Okay. So we have a common ranking. The range is determined on the common ranking, to which the agents, so the agents can only be matched to objects within that range. And however, once that range is given, within that, agents are free to order the object. By the way, you can ask me questions anytime. So basically, so just to give some interpretations of the model. So first of all, we have this compatibility or eligibility. So probably the acceptance, yeah. So we were kind of already working, for years on this project, and we realized we call it acceptance interval, but actually neither acceptance nor interval is probably the best phrase here. But anyway, so when we are saying acceptance, it doesn't just have to necessarily be based on the agent's preferences. And in fact, we are assuming that this is publicly known, right? What's acceptable. So it's probably better if you interpret it as some sort of a compatibility or eligibility, which can be verified or is given exogenously. Okay. And then we could also say, well, maybe it's self-imposed by the agent because we have bounded rationality. We have too many options, and if we want to, come up with a strict ordering, then it's best to first rely on some sort of a given information about the different options and just limit ourselves to a certain range within that. And then we only rank those. And so, and by the way, you can see that these can also be connected. So, maybe you are only compatible with a certain range. So why should you bother, ranking other alternatives and so on? Or it could be just based on constant information acquisition, which is, again, it is related to the bounded rationality criterion, motivation, I guess, as well. So here we could say, of course, it's not explicitly modeled here, but we could say that agents restrict themselves to a certain range. And then within that range, they are going to acquire information to be able to come up with a strict ranking, such as going for a campus visit or having an interview and so on. Yeah. Kind of just the motivation. And here are some applications just quickly to throw these out there. So these applications, I mean, the model doesn't necessarily capture, everything. In fact, it doesn't capture everything, but just to give you some idea of what we had in mind. So for example, entry-level job market. So we have applicants who are ranked according to some criterion, and then the employers choose within a range. And then there is an interview, which determines the employer's ranking within that range. Okay, interviews. And it's not feasible to interview everyone, right? Other ideas or other applications could be child adoption, although it's a bit more dynamic. Usually, we are looking at a static model here, but we could say, let's say, if it were a static sort of matching problem, is that families are only eligible for a certain age range of children, and then within their age range, right, they can meet with the children and rank them, give their preferences. For college applications, we have university rankings, and within a certain range of the rankings, students can rank them. For example, they can do campus visits and so on. So that's just very quickly, but basically we didn't mean to capture the details of any of these applications. We think of our model as something very simple, like a starting point. And we think that this is the first study, and we haven't come across another one, where we are looking at this kind of consecutive acceptance intervals. And yeah, so in our model, it's a one-sided model, so we have two sides, right? But objects have no preferences. We assume strict preferences for the agents. And we also assume that interval profile is publicly known or verifiable. So this is mostly interesting for the strategic issues, and I'm actually not going to focus much on that. So we have results in the paper that I'm not going to present, but a lot of them almost immediately follow from what we already know, and we can just add these additional results on strategic proofness and so on. So without this assumption, we definitely wouldn't have that, right? So if we ask agents to reveal their acceptance, the range of acceptance, then we wouldn't have any of those nice incentive results. So just to point that out. And so the main questions that we are looking at is here, whether we can take advantage of the special structure of these consecutive acceptance intervals. Oh yeah, and why is the interval, right? So these are discrete objects, right? So, but anyway, we refer to these as intervals, such that we could simplify the algorithms, and also can we, how do these results compare when we look at arbitrary acceptance sets? Okay. And here I will mostly focus in this talk, I will focus on, and this is actually the focus of the paper, so I'm not just presenting some not so interesting part of the paper, and I think I'm presenting the most interesting part. So I will focus here on the maximum and Pareto-optimal matchings. Okay, question?
Yeah, just a small question. I'm not so familiar with like the vocabulary here. I was wondering, when you say it's a one-sided model where objects have no preference, like in the example of the entry-level jobs, then it would mean that like the people applying would basically accept any job. Is it?
Yeah. So exactly. Yeah. So that's partly why I'm saying that. This is a very simple setup, so it's just kind of a first approach. So it actually doesn't really capture, because a lot of applications you would have preferences on both sides, or you would have what we call priorities, let's say on the object side. But so we are kind of not dealing with that. So we are saying,
okay,
that, so it doesn't capture, that's right. But one-sided, so it can be a bit confusing because we could also call one-sided something like a roommate model. So that's not the case here. So we have agents on one side of the market and objects on the other side. But for some reason, very confusing, we call this one-sided models because we only have agents on one side. And so we only care typically about the agent's welfare. And there is only an incentive consideration for agents.
Perhaps like one-sided bipartite model.
Yeah, it is bipartite, exactly. Okay, so the model, so we have a set of agents, we have a set of objects, and the objects have this common ranking. And then if we have a consecutive acceptance interval for an agent, then it will be consecutive according to the common ranking. So we can talk about an acceptance profile, and this is what we assume is public information. And when acceptance sets are consecutive, then it is an interval profile. And we also have a preference profile, which is, we consider this private information, and there's a strict preference of each agent over the acceptable range.
So basically, it's a reshuffling of the acceptance profile, right? The preference profile.
Reshuffling? Oh, you mean, yeah, it's an ordering over, yes. That's what you mean, yes. Okay. So what's a matching? be clear to everyone, but anyway, so it's an assignment of objects to agents. So each agent gets here at most one object, and the same object cannot be assigned to more than one agent. And an object that is assigned to an agent has to be in that acceptance range or the acceptance set. The matching rule is a function which assigns a matching to each reference profile. Oh, sorry, I have this in the slides. It's a bit, so this there's no line here. Sorry, there may be some typos. These are pretty fresh, so I have a chance to get rid of all the typos, but please ask if there's something really confusing. Okay, so matching is maximum if there is no other matching, which matches more agents and objects. So basically, we are asking for maximum cardinality. And note that the cardinality does not depend on the preferences, strict preferences, right? It only depends on the interval profile or the acceptance profile. And the matching rule is maximum if it assigns a maximum matching to each preference profile. So I'm just introducing the main axioms here. The next one is Pareto-optimality. I don't know if everyone is familiar with this. So we say that a matching or any outcome is Pareto dominated if there is another outcome which doesn't harm any of the agents and makes at least one agent better off. And if it's not Pareto dominated, the matching is not Pareto dominated, then it's Pareto-optimal. And so we are interested here in matching rules, which are Pareto-optimal in the sense that they assign a Pareto-optimal matching to each preference profile. Yeah, and so in our model, actually, maximum and Pareto-optimality are independent of each other. That's not necessarily true in any model. But however, there is always a maximum and Pareto-optimal matching. So because, yeah, so we have a finite set of matchings, so we can always find the maximum matchings, and then we can just Pareto improve upon them. That is, we can keep if it's Pareto dominated, then we can find another matching which Pareto dominates it, and so on, and we can keep doing this until we reach a Pareto-optimal matching, right? And it is going to be maximum because we started from a maximum matching. Okay. So yeah, so these axioms. So yeah, I'm not going to talk much about these. But anyway, so basically in the paper, we also look at strategy proofness. So that's where the public knowledge of the common ranking is important. So strategy proofness means that there is no incentive to manipulate. That is reporting the true preferences in a direct revelation game is a weakly dominant strategy. You cannot do any better regardless of what the other agents report. Right? And you could do worse if you reported something else. Okay. And neutrality, again, I'm not going to work with this a lot, but sort of just for motivation. So matching rule is neutral if it treats the objects symmetrically. So the objects labels do not matter. Okay, so so first about maximum matchings with consecutive acceptance intervals. So here is a rule which gives us a maximum matching at every profile, acceptance profile. So we start with the first object in the common ranking. And by the way, it's very intuitive, I think, I hope. So we start with the first object in the common ranking, and then we consider all the agents who have that object in their acceptance set. And we give it to the agent who has the fewest number of objects in their acceptance set, whose acceptance set contains the object. And if we have more than one of these agents, right, same number of objects, doesn't have to be the same object, then we break the ties according to some pre-specified permutation of the agents. Okay. And the object remains unassigned, right, if there is no agent who has the object in their acceptance interval, clearly. So now we remove this object and agent, and then we repeat with the next object in the common ranking, and so on.
What is the assumption about the capacities of the objects?
Yeah, that's a good question. So in general, so we didn't really, by capacity, you mean, oh.
Like the objects can be matched to several
Sorry. Yeah, I guess it was a different question. Yeah, no. So here it's one-to-one. So each object can be matched to at most one agent. Yeah. But we have some issues actually now that you brought that up. We have some issues about how many objects versus agents and how many are acceptable. So actually our results really simplify, and for the most part, let's see, good to know. But anyway, so I'm presenting some results which would be more complicated, but only technically. So we can extend all the results, but it's a very convenient assumption here to say that we have enough objects, and the acceptance profile is such that each agent can be assigned an object. Okay, so if we make that assumption, we get rid of the kind of things which are in some sense trivial, but add extra technical complications, where let's say we have 5 agents who only have the same 2 objects in their acceptance set, right? So then clearly only 2 of these can be given an object, the other 3, we have to get rid of, and we have to take care of these cases. So if we make that assumption, then we don't need to worry about those cases. But it's not so it's not an essential assumption in the sense that otherwise the results don't go through. That kind of assumption. Okay, so the consecutive maximum rule, I'm referring to it as singular, although well it depends on the tie breaking, right? So in fact it's a class, but anyway. The consecutive maximum rule is a maximum rule for consecutive acceptance sets, and it only depends on the interval profile, right? The consecutive acceptance profile, and it doesn't use, right? So in general, we would either need some sort of an augmenting path, right, to find the maximum matching. It's basically a greedy algorithm, right? And what makes it possible is this consecutiveness of the acceptance intervals. And in fact, if we use a different ordering of the objects, right, we would not necessarily end up with a maximum matching. Okay, so we need to use the common ranking. Okay. Last line covered. All right. Yes, of course.
So basically, like this consecutive maximum rule follows the ranking, the common prior, basically. Like when the common ranking. Yeah. And we could try to assign every student, well, every applicant without them. Okay.
Right. So I will show you. Oh, yeah. First, an example. So here, so we have the common ranking, which is A, B, C, D, E, and this is an acceptance profile, right? So these are not strict rankings, right? So I just put, so anyone who has A, right, I put in the first row, anyone who has B, second row, and so on. So this is just the acceptance set, and it's consecutive, right, because we have A, B, C, D, E, and we don't have a hole anywhere. And so the consecutive maximum rule here, so it starts at A, right? So it picks for A, it picks 1. So the 2 candidates are 1 and 3, but we have the tie breaking rule, right? So based on that, so it's 1, 2, 3, 4, 5. So 1 is going to be assigned A. Now for B, then we have, so we get rid of A, right? So for B, we have 3, who has the smallest and the fewest objects. And in fact, it's just B, so 3 gets B. The next one in the common ranking is C. So now 1 and 3 are gone, and also objects A and B. So we are just looking at this here. And so we have 2 and 5 who are candidates for assigning C. So now we have to go to the tie breaking. So this gives us 2. And then we have, so now, A, B, C are gone. So we only have, D and E remaining. And so 5 gets D. He has fewer, right, than the other agent, and 4 gets E.
So if we take the opposite permutation, basically, like we get a matching of 3.
Sorry, if we take the opposite.
If we start from 5, from student 5 instead of student 1.
Oh, yeah. So then we could get a different matching. Yeah. Yes, that's right. But it will still be maximum.
But it would be, I think, and maybe, okay.
Yeah, so the rule says that you need to take the agent with the fewest objects in their acceptance set, right? So you don't just go in the order. So that's really, really important that you look at the smallest acceptance set. Otherwise, it will not be the maximum.
The permutation of tiebreaking is fixed for all the tiebreakers. Is it important for the maximum property, or if you use if you choose randomly every time, would it matter? Or
yeah, it wouldn't matter here. So for any profile, yeah, you can use any tiebreaking. But we define the rule, you know, to be a bit consistent. So we have, yeah. So where would it matter? Let's see. I think it wouldn't matter in general because we don't have incentive. So for if we had incentive properties, but here not looking at incentives, then it could matter that we are using a consistent time breaking. But for this result, it doesn't matter. Thanks for finding that out. Okay, so that's the consecutive maximum rule, and so it turns out that we can also find it in the following way. We can order the agents, and we call this the consecutive agent ordering. So basically, and this is again because we can only do this because they have the consecutive acceptance intervals, right? So we order them lexicographically. First, we look at their last object according to the common ranking, and and the agents who have a last object which comes before, right? Which is the the smallest in the common ranking, or which comes first, I guess, in the common ranking. Those agents would be first in this agent ordering. So I call it last object first. Yes. Hopefully this is intuitive enough. And so if agents die, which clearly they can, because they can have the same last object, right, in their acceptance set, then we will apply the first object last. So then we look at what is their first object in the range, right, in the common ranking. And whoever has the latest, right, as we proceed in the common ranking, those agents will be ordered before the ones the ones in the order whose first object comes earlier. Okay. Hopefully this is clear. So basically what these two imply is that if an agent has a fixed subset of the acceptance range of some other agent, then this agent is going to come before the one with the smaller subset will come before the one with the larger subset. Okay. And then we also need tie breaking because we could have the exact same, right? For two agents and have the same acceptance interval, then they will, we will sort them out again based on some fixed permutation of the agents. Okay, so this gives us then a specific ordering of the agents. And so it turns out that we can give an alternative definition of this consecutive maximum rule, which is basically that, and it's based on this consecutive agent ordering, and it's basically assigns the agents in the order of this consecutive agent ordering. The first object in the, so we take the consecutive agent ordering and we assign in that order, and we give each the first object in the common ranking, which has not been assigned, not yet been assigned. Okay. All right. So yeah, and this is for, I'm going to show you an example, but this is sort of to motivate to some extent the next step. So the consecutive maximum rule does not find all maximum matchings. Okay, so even if we consider all the different agent permutations, that's not true. So for example, we could have, let's say, AB in one acceptance set and ABC another. And if A comes before B in the common ranking, then the first agent will always get A and the second agent will always get B. We cannot reverse that. So this would suggest, right, so now I'm kind of motivating the next step, but this would suggest that we should look at different object orderings. But remember that here we are looking at the common ranking. So anyway, but before I do that, so let me show you the example. So here, so this is the same example that we've seen before, but now I sorted the acceptance set according to the consecutive agent ordering here. So we have AB first, and then 1 comes before 3 because of the tie breaking, so on. Notice here, so 2 comes before 5 because although they end with the same object, but 2's start later, and so on. And finally, we have 4 comes last because 4's last object is the latest in the last one in the common ranking. And so once we sorted them this way, then notice that here in this example, and this is, for example, where it comes handy if we assume, for example, that each agent gets assigned an object, because then the assignment will be exactly on the diagonal like here. But more generally, it doesn't have to be like that.
So we're assuming basically that when we only truncate this preference list, we do not cut it in the middle. Like we cannot have like A, B, D. We can only have A, B, C, D.
Yes, yeah. So consecutiveness means that we have to, we cannot have a 4.
Okay, exactly.
Acceptance. That's the picture we are using here. Okay, or we did, but now we are going to maximum matching with arbitrary acceptance sets. So for comparison, so basically, we are looking at just any acceptance set now, and we will need the definition of an O block. So an O block for a given acceptance profile consists of K agents and K objects, such that the K objects are in the acceptance set of all K agents, and these are the only, and the objects are only in the acceptance sets of these K agents. Okay, so the objects are not. So we call this an O block, and at the very end, if I get to it, I will define an I block, but just to sort of tell you why. So O block refers to the fact that the objects are vulnerable to some extent to not being assigned, okay? Because, so these K objects can only be assigned to these K agents, right? And then if I get to it, so the I block will be similar, but kind of the opposite. So it will also be K agents, K objects, but there the agents will be vulnerable. So basically, the agents will not have anything else in their acceptance set, only those K objects, and then the agents can only be assigned those K objects. But so here, this is not true, right? So actually, these agents can have other objects in their acceptance sets as well. Okay? But these objects are not in the acceptance sets of any other agents. So that's an O block. And so a general maximum rule is similar to a consecutive maximum rule, except, well, it's quite different. So first of all, you can use an arbitrary ordering of the objects. Okay, so now we are not sticking with the common ranking. Okay? In fact, because the common ranking is irrelevant, right? Because we have arbitrary acceptance sets. And this is, remember, I was trying to motivate this a little bit also, not just by saying that we are now looking at arbitrary acceptance sets, but also to be able to find all maximum matchings, right? So if we do this, I'll say here, and then we can find all maximum matchings. And however, now it's not just a straightforward read the algorithm. We actually have to change the order of the objects depending on these O blocks. Otherwise, we may not end up with a maximum matching. Okay. So if in any step there is an O block, then the objects in the O block are assigned first, and hopefully it's intuitive why. Because if you don't assign them, then actually those objects, some of those, at least one object from the O block may not be assigned, right? And then that's not going to necessarily lead to a maximum matching. Okay. So yeah, so basically we are altering the object ordering by using these O blocks to ensure maximum matching. Yes.
Can there be a conflict between O blocks? Like if you have two O blocks at the same time, couldn't you share about taking into account several of them?
Yeah. So you mean overlapping O blocks?
Yes.
Yeah. So yeah. That's a good question. So I guess because they are going in a certain ordering of the objects. So we are going to pick those objects which come first in the ordering.
But an object can be in several O blocks, right?
No. So each object can only be in one O block. That's right. Yeah.
So it's like a partition.
But so it is true that there could be more objects acceptable. So we could have k agents, and let's say they have k plus 1 objects. Is that right? Yeah. Yeah, let's say k plus 1 objects which are only in the agents, those agents acceptance sets. So then one of those objects we will not be able to assign, and which one will be determined by the ordering of the objects. Some of these, we've been working on this for a while. Some of these I haven't seen for a while. So anyway, so yeah, so general maximum rules are maximum rules for arbitrary acceptance sets. And here is the theorem which tells us that actually this way we can find all maximum matchings. Right? So if we fix an arbitrary acceptance profile, then for each maximum matching at this profile, there exists an ordering of the objects, such that the general maximum rule using this ordering of the objects yields the maximum matching in question. Okay. So now here, by the way, I talked about, yeah, I should maybe slightly clarify. So here I'm referring to general maximum rules in you know, as in a class of rules, because it can use any ordering of the objects, but actually it really also depends on the time breaking. So now we have an object ordering, which is the primary sort of the primary way to identify a general maximum rule, but there is also the tie breaking, which is an agent permutation. But it's secondary, that's important. And so we only use it for tie breaking. Okay, so just to quickly show you an example, before we move on soon. So let's say the arbitrary ordering of the objects is BCAD, right? Or in fact, well, any ordering, because so here's an example, right, where we have a whole, right? So there is no way to order ABC, right? You can see in a way that there is no whole, at least for one agent, right, in the acceptance set. Okay, so this is such an example. And so here, so we start with B. So the ordering is BCAD. B is assigned to 1 because the two agents who have B in their acceptance interval are 1 and 3, and so 1 has fewer objects. And now step 2, so now we're supposed to assign C. But now what happens? So C would be assigned to 2 just based on the tie breaking, right? Because now, so B is already assigned, right? And we have A has A and C, and 3 has C and D. And so C is in both of these, but the tie breaking actually tells us to give it to 2. Right now, it could go the other way as well, but anyway. But now what happens is if we give C to 2, then we can see that we are not going to have a maximum matching because A is going to remain unassigned. And we can actually come up with an assignment which assigns all 4 objects. Right? Okay. So this is where we need to rely on the O block. Right? And in fact, we can see that A2 and A form an O block, the simplest possibility for an O block, which is that A is now only into this acceptance set. Okay. So hence we are going to assign A to 2, and now we are still on track for a maximum matching. And then C can be assigned to 3, that should be, and B is assigned to 4. And we have a maximum matching. But it would not have been possible without altering the original ordering. So we have A, then C instead of C, then A. And that's due to the O block. Okay, so now we are going to look at maximum and Pareto-optimal matching. And this is with arbitrary acceptance sets. So strangely enough, our somehow, yeah, so initially, so we set out actually to work with well, obviously the consecutive acceptance sets, but we ended up with results which turned out to be for arbitrary acceptance sets. And so right now we are looking for sort of simplifications. And I think, well, we have some conjectures anyway. But so I will show you for arbitrary acceptance sets what we have. So first of all, just to sort of clarify that we are narrowing this down, and we could use, so this is where we could use neutrality or OSP implementability. You're probably not that familiar with this. So this is a somewhat new result. Yeah, a very influential paper in 2017. And it basically says that agents are cognitively limited and strategy proofness is not enough. We need more straightforward, more transparent mechanisms, right? Because agents cannot use contingent reasoning. So that could be another motivation, or we could say we want neutrality for the rule and so on. But so just to sort of clarify, so we are aware that we could just simply take a maximum matching and use those as endowments and then use a top trading. So a top trading cycle. If you're not familiar with this, it's basically we just ask agents to point to the agent who is endowed with their highest strength object. We identify cycles and we assign those agents in the cycles the object, their most preferred object. We remove them and then we keep iterating that. Okay, so this would actually give us a maximum, a Pareto-optimal matching, and the rule itself is actually going to be a strategy proof. In fact, group strategy proof, which is a stronger property, even groups can manipulate. So this is pretty nice, but that's not what we wanted to focus on. We wanted to sort of stick with these simple greedy algorithms like serial dictatorship. Okay. So what's a serial dictatorship? Yeah, it's a very severe name. So there are some attempts in the literature to change it to priority rules and whatnot. And I don't know how you know them, maybe. But the literature that I'm familiar with, it's always been called serial dictatorship, which is a horrible name. So it kind of comes from voting environments, right? There is a dictator, but here it's serially dictatorial. But anyway, serial is not necessarily such a... Well, anyway, so basically a serial dictatorship is really simple. It just says we line up the agents and we give them their favorite object in that order, of course, subject to feasibility of the objects being available. And serial dictatorships are Pareto-optimal by definition, and these are neutral, right? So they treat the objects symmetrically. The labels of the objects don't matter. That's not true for the trading rules, right? Because you have those endowments. And it's also actually OSP implementable. So it meets an even stricter criterion than just strategy proofness or group strategy proofness. So it's something that agents can deal with cognitively because it's very transparent. Yeah. So yeah, first an impossibility. So given an arbitrary consecutive acceptance profile, and notice that this is about consecutive. So it's not just any. Right? So given a consecutive acceptance profile, it may not be the case that there is a serial dictatorship which is maximum. Okay, so I don't know if, if this is clear. And so first glance. So basically, if you allow agents to pick their favorite object, right, then if you just, and this is even true for consecutive, which I have an example, I'll show you that. Then we may not end up with a maximum. So here is a very simple example. So these don't have to be super complicated. Okay? And also, as far as I can tell, at a first glance, I mean, I would have no idea. Maybe somebody would, but so I would have no idea why this wouldn't work. Okay, but it doesn't. And in fact, it looks kind of asymmetric. So even if I add the B here, it still doesn't work. Okay, in the following sense, so pick any of these agents, right? Then it is the case at this acceptance profile, and it is consecutive, as you can see. Then it is the case that the other three agents can pick all of the objects in this agent's acceptance set if they were to go first in the serial dictatorship before this agent. Okay, so any one of these. So let's say I pick one. Then ABC could be taken if, let's say, 2 ranks A first and 3 ranks C first and 4 ranks B first, then they just picked A, B, C, and there will be nothing left for 1 if 1 goes last in the serial dictatorship. Okay? And this is true for all of the agents here, right? So no matter which one you choose, the other 3 agents, depending on their preferences, could have picked all of the objects in the acceptance set of that agent. So if the agent goes last, then they will not have any object left. And yet we know, right, A, B, C, D, we know that in a maximal matching, we can assign all 4. Okay. All right. So yeah, we call this unsolvable in that particular sense, this kind of profile. Okay. So let me define fully flexible agents. I'm doing this time. Anyway, so fully flexible agent is basically somebody, an agent who has, actually, let me start with the competing agent. I think that's more intuitive. So basically, we can say that each agent has competing agents, while the agents who have at least one object that overlaps with their acceptance set, right? So if there is any overlap with some other agent, then we call that a competing agent. And so basically this says that there are fewer competing agents for a fully flexible agent. There are fewer competing agents in the acceptance set of the agent than the objects in the acceptance set for the agent. Okay, so okay, so what does this mean? So basically, you can see intuitively, such an agent is flexible in the sense that if this agent went last in the permutation, they would still have at least one object remaining, right? Because they don't have enough competitors, right, for those objects based on the acceptance set. Okay. So that's a fully flexible agent, and now a flexible agent is actually just a generalization of this. So notice that actually it doesn't have to be the case that the entire acceptance set of the agent should have fewer competing agents. It's enough to have a subset, right? If I have a subset of my acceptable objects, right, or whatever, compatible or eligible objects, such that I have fewer competitors than the number of objects in that subset, that's already enough for me to be sure, right, that I will be assigned an object no matter where I am in the agent permutation. Okay, so that's a flexible agent. And notice that actually all the agents are also flexible agents in an O block, right? So why is that? Because in an O block there are exactly k-1 competing agents, and so all of the agents in the O block are going to be flexible agents.
Wouldn't it be enough to just say that if it's less than the number?
But if it's equal, so the competing agents are the other agents who are competing. So if it's equal, then they could pick all of them, right? So it has to be at least one less.
Oh, right, excluding itself.
Yeah, so if I have 4 objects and I have 4 competing agents, and they could just, if they all come before me and pick exactly those 4, then I'm out, right? Yeah. But if I only have 3, then they can pick whatever they want because I will still have 1 left. So yeah, it has to be strict. Okay, so what's a solvable acceptance profile? It's an acceptance profile for which we can remove all the agents iteratively just by removing these flexible agents. So we look at the profile and we find that there is a flexible agent, we remove it. Then we look at the reduced profile, right? So we only remove agents, by the way, we don't remove objects. Right? But when we remove agents, we are removing competing agents, right? And strongly solvable, so basically here we are, so we kind of started with this, but we realized that it doesn't give us all the possibilities, but so it's easier to identify fully flexible and O-block agents. So if we can do that, then we just go with that. So those are strongly solvable acceptance profile. And oh yeah, so actually, yeah. So in the unsolvable profile example, there is no flexible agent. which I can jump back for a second, but I'm afraid that I'll be out of time really soon. But yeah, so there is no flexible agent here. However, you look at even the subset, there is always at least as many competing agents as for the number of the objects in that subset of the acceptance set. Okay, so it's not by its, like you would have to do, look for a while. It's not instantaneous, but you realize that that's the case. Okay, so now we have a characterization of the acceptance profiles for which a maximum serial dictatorship exists. Okay, and so basically it's just in terms of these solvable acceptance profile, right? So there exists a serial dictatorship which is maximum for an acceptance profile if and only if it is solvable, right? So we know that it's not true for an arbitrary acceptance profile, that we can always find some permutation of the agents for which, regardless of the strict preferences, they can always find a maximum matching. But it is true for these solvable profiles, right? Which I think, why. So one direction, the easy direction, should be relatively intuitive, right? Because as we remove those flexible agents, so those agents, so basically we go in a backward order. That's where I'm going next. So we could remove, so the first flexible agent that we remove, that agent can go last in the permutation. And then if we have a flexible agent after that, right, in the next step, then that agent can go before that agent and so on. And so basically this way we can figure out all the agent permutations which work, okay? And we call these block serial dictatorships. Okay? And so basically what we have is, so there are interchangeable agents. So those are the agents who are removed in the same step of the procedure. And if we want to get all the different block serial dictatorships, all the different permutations, then we have to remove all of the flexible agents that are there already in every step. Okay, so this is, so otherwise it's not important. By the way, you could go one by one, right? If you just care about removing flexible agents, but if you want to figure out all the agent permutations, you have to remove all of them at the same time. Okay, and so here we have so this field, so yeah, let me say that actually it doesn't give us, strictly speaking, all the agent permutations, what we call the block serial dictatorships that work, but all the others are outcome equivalent. Okay, so the ones that we don't capture this way are the ones where two agents actually don't have a common object in their acceptance sets. And so then we can freely interchange them, right? But we may not capture that in this procedure where we move iteratively these flexible agents. Okay? So there are actually additional permutations that work, but they don't give us additional outcomes, okay? Additional matchings. Okay, so block serial dictatorships, so that's why I'm saying essentially they capture all the agent permutations, essentially in the sense of outcome ones. And now, here is an example just to see how this works, right? So this is a strongly solvable, and notice, by the way, compared to the unsolvable, I only remove the 2 from here. Okay, so actually having more acceptable, right? So it's really about the configuration, right? So having, strictly more acceptable objects is not necessarily better in this context. Okay. And in fact, here, if I add a B to both of these, it looks nice and symmetric, still not solvable. But this one is solvable. So in step 1, agents 1 and 2 form an O block with objects A and B. And so objects A and B can only be given to 1 and 2. And then in step 2, agents 3 and 4 form an O block. Right? So in step 1, they don't have the O block. Right? In fact, this is what I call an I block. That won't confuse you. But anyway, so let's stick with the O blocks. So, so we have an O block here. So they get A and B, 1 and 2, and then agents 3 and 4. And so we are able to remove all the agents, right, in O blocks, which means that these are flexible agents. So this is solvable. And what are the agent permutations that work, right? That is for the block serial dictatorships. It's basically, So we removed first agents 1 and 2, and remember that we have to go in the reverse order. So 1 and 2 go last, and 3 and 4 come first. And here, just to explain, so the square bracket means that within that the agents are interchangeable. So basically, those are the agents that are removed in the same step. So basically here, we will have 4, 3, 2, 1, and so on. That's one. And these can give different matchings. Okay. So that's strongly solvable. And then another example is solvable, but not strongly solvable. And again, consecutive acceptance profile, just to demonstrate that this exists. We need the solvability. So here, there is no fully flexible agent or O block to begin with. Right? However, we do have a flexible agent with 2 for A, B, and C. And so we can't include D because D gives a lot of competition. But for A, B, C, the 2 competitors are just 1 and 3. Okay. So we remove agent 2. And now this leads to agent 1 forming an O block with A, and agent 3 forming an O block with C. So we can remove them, right? Because now they don't have the competitor 2. So we can remove agents 1 and 3. And then in the last step, we can remove agents 4 and 5, who now have an O block with D and E, right? But before they didn't have it because D and E were acceptable to some other agents as well. So we can remove all of them. So it's solvable, but it's not strongly solvable because we didn't have a fully flexible agent or an O block at the beginning. Yes.
I don't understand why your agent is not fully flexible.
Why not? Because agent 2 has 4 competitors and has 4 objects in his acceptance set.
There is no way. There is no objectives for agent 2.
But that's a kind of opposite.
Yeah. So that's because agent 2 is a flexible agent, but not fully flexible.
But flexible means it is flexible for subsets, but.
Yeah, so full flexibility would require that when we look at the competitors for the entire acceptance set, we have fewer. Right?
So it does not require that the competitors are different. Because here.
Well, so that's why we have the flexible. You are exactly referring to the flexibility. So you are right, it's the terminology. So flexible agents are agents who can go last because they always get an object, no matter what the others pick. But it doesn't mean that they are fully flexible. So I think that's what I mean. All right. So yeah, and yeah, okay. Okay, so I actually don't have much. It's just conjecture for the research, and I already kind of referred to this a little bit. So an I block, I think I have one more slide. So an I block is basically, as I already sort of described it before, again, it's key objects, key agents, but in this case, it is the agents who are vulnerable. So the agents are not in other objects. The agents don't have other objects in their acceptance set, right? Just these key objects. So the agents will only be assigned objects if they get these key objects. So it's kind of, so that's why, so we call, the name basically reflects who is vulnerable, right, in that sense of remaining unmatched. And so this is a conjecture. So actually, it's not necessarily that it's difficult to figure this out, we just didn't really get a chance. So we are kind of hoping that this is true, but who knows? So this, by the way, this whole project, so we had like 27 different conjectures before we ever got started on it, which are all wrong. So I'm just saying, but anyway, so in that sense, but hopefully so far what we could see. So we are kind of conjecturing here that if a consecutive acceptance profile, so this is specifically for consecutive. So we are now trying to simplify results based on the consecutive acceptance sets, right? So we have the general results and we are trying to see if we could find nicer, simpler results when we have consecutive acceptance profiles. Okay. So basically here, we are conjecturing that a consecutive acceptance profile is solvable. Then we can find a maximum Pareto-optimal matching. So by the way, it doesn't find all the maximums, right? But first by assigning objects to agents in I blocks iteratively. So these are the vulnerable agents. And then for the remaining ones, we just do the consecutive agent ordering and we assign objects to them in that order. So this would be, so the serial dictatorship would start with agents in the I blocks, but we may have to iterate that. And then we use the consecutive agent ordering. And of course, we'd also like to know whether we could simplify the definition of solvable acceptance profiles when the acceptance profile is consecutive. So actually, I think this is my last slide. Yeah, so I'm done. Okay.